Hey, everybody. It's Friday, April 23rd, and our goal for today's video is going to be to review the free response question that was assigned yesterday, listed as FRQ Review Day 7, the experimental design question. Now, I like this question. I figured it would be a good question for us to look at to sort of wade into the experimental design portion of our review, because this one, more than a lot of them, is fairly straightforward. This one here says a projectile launcher consists of a spring with an attached plate, as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any of three positions A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon the release of the pin. So you pull the pin out, obviously the spring is free to decompress, and the sphere flies out. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. Now, the second part of the question, or I should say the first part of the question, sorry. The first part of the question says the student plans to test the hypothesis by launching the sphere. Notice there it says using the launcher. Now, there's a reason why they underlined this here, using the launcher. You are not supposed to use any other method for determining the spring constant that doesn't really involve the sphere being launched. The way that they want you to measure the spring constant has to involve the sphere being launched. So part 1 says state a basic physics principle or law the student could use in designing the experiment to test the hypothesis. And then the second part says using the principle or law that you state in part A1, determine the expression for the spring constant in terms of the quantities that can be obtained for measurement with equipment usually found in a high school physics lab. Now, there are a couple things I want to say here before we really get into this. The first part, I think, is whenever they tell you in an experimental design question that a student hypothesizes something, you really want to just take a moment to evaluate the hypothesis. Is this kid right or is this kid wrong? Because that really sort of sets up the flow for the whole experiment. Because if the kid is saying something that's obviously wrong, you got to prove them wrong. And if the kid is saying something right, then you got to prove them right. So what this kid is saying is the spring constant of the spring inside the launcher is the same depending on different compression distances. Now, if you really take a moment to evaluate what the kid is saying, essentially what they're saying here is this kid is hypothesizing that the spring constant is constant. Hello? That's correct. The spring constant is constant. So no matter how far you compress the spring constant is going to be the same number. The compression distance is going to be different. That means the force and the energy stored in the spring is going to be different at different compression distances, but the spring constant will not. So keeping in mind that we have to launch the sphere, there are a couple of options that we have for the basic physics principle or law that could be used in designing the experiment. The way I see it, the most obvious law to use for part 1 is going to be conservation of energy. Here, if we launch this sphere, we can do this in such a way that we could apply conservation of energy to be able to measure the spring constant of the spring. Conservation of energy, to me, seems like the most obvious way to approach this problem, particularly because part 2, which is now saying use that principle to derive an equation for K, is very easy using conservation of energy, because all you have to do here is just set up your energy equation. The initial energy is equal to the final energy, and go from there. Now, I think it would be important to discuss one thing before we show the equation. And the thing that we should probably discuss here is that there are multiple ways to design this experiment that are realistic. You can shoot the sphere out of the barrel and position a photo gate at the end of the barrel to measure the speed. Now, in some cases, that might not be practical, because despite the fact that you've probably never seen a photo gate in person, the space here between the two poles of the photo gate I would estimate is probably only 3 or 4 inches wide. So it is just a reality of the situation that you can't use a photo gate to measure the speed of something that's wider than the gate. Like, that's just a reality of the situation. Having said that, you could, if you wanted to, put a motion sensor right in front of the barrel here and use that to measure the exit velocity of the sphere. Now, of course, the challenge with this method is that the second the sphere leaves the barrel, it's going to start to accelerate due to gravity and will not move in a straight line. Those are some challenges. It is acceptable to use this method, but you have to put the motion sensor or the photo gate very close to the barrel. Of course, another method, which sort of gets around this problem, is that you could put the launcher on a table and launch the sphere and basically treat this like a projectile motion problem where, and now this table edge really should probably be at the very edge of the barrel, but just go with it here for a minute. You can use the range for the projectile along with the height, which you can use to determine the time, right? So the time would be given by 2 delta y over ay for horizontal projectile. And then the range equation is delta x equals v naught x times t. So you can determine the launch velocity by basically using the range and the time. And so that would be another totally viable method for this experiment. A third method, which is actually, in my opinion, the preferred method, just because it's easier to talk about analyzing and measuring, but we'll get to that in a minute. The third method is shooting the sphere straight up in the air, taking the launcher and orienting it vertically such that the sphere is just going to go straight up into the air. Because when the sphere stops at the maximum height, all of the energy is gravitational potential energy. So basically, the elastic potential energy that's present in the spring is turning into gravitational potential energy at the end. Whereas in these two equations, the elastic potential energy is converting into kinetic energy. Both of these options, though, it should be noted, are viable. Now, some of you might be thinking, why are you talking about the experimental design part when we're still answering the part before that? You have to sort of start to do some planning for these experimental design questions in the beginning. It's good to think about this stuff before you start answering, so all of the parts of your answer flow together. Now, because I'm assuming many of you did this different ways, I'll just show both of these for now. And so if you decided to use the idea that this thing is going to be in motion afterwards, so the elastic potential energy is converted to kinetic energy at the end, then your equation is going to be 1/2 kx squared equals 1/2 mv squared. And of course, in a potential spring potential to kinetic energy transformation here, the halves cancel. And so when you solve this for v, sorry, you're not solving this for v, you're solving this for k. Hello, that's the point of the question here. We are getting k is equal to mv squared over x squared. Now, as I mentioned, in any experimental design question, the equation is key. So notice how they're setting you up here for this. Everything is going to flow from this equation. And that's why doing that pre-planning here in the beginning is really important. If you use the idea that this thing is going to gain some height at the end, then your equation is going to look like this, where the initial elastic potential energy is equal to the final gravitational potential energy. And so you get the equation 1/2 kx squared is going to be equal to mg delta y, where the k equation then at the end is going to be 2. You got to multiply both sides by 2 here. So we get 2 mg delta y, and then we've got to divide by x squared. Remember, every measurement you make needs to be of the things that are in this equation. And so whichever one you use, this is setting you up for the whole thing here. Take a second to pause this video and make sure you have this written down in your work. And when you hit play, we'll take a look at the scoring guide. All right, so the scoring guide for this part looks like this. There were 3 points for parts A1 and A2. It says an equation that is consistent with a relevant principle or law as written in A1, a valid equation that contains measurable quantities and includes the spring constant, and then a correct and valid expression for spring constant. This expression must be solved for K. Now, there are a couple things we have to say about this. In my example here, using two examples actually, I talked about conservation of energy. I think a big question here could be, could you use Hooke's law? Because if you put a motion sensor here at the edge of the barrel, you would get a graph of velocity versus time. And you could use a graph of velocity versus time to determine acceleration, which would allow you to find the spring force. And then, of course, you could use the equation Fs equals Kx, which if you solved it for K, you'd get Fs over X for the spring constant. It's moderately plausible. The problem is this experiment would be pretty complicated because if you got a graph of velocity versus time, it would end up looking like this. It would not be a straight line. The reason why, of course, is because the spring force is directly proportional to the displacement. So as the spring decompressed itself, the force would be getting smaller and smaller and smaller. And so the acceleration would be getting smaller and smaller and smaller. Now, you could use the graph to determine the average acceleration and then use that to determine the average force. And because this spring is going to decompress until eventually x equals 0, the actual spring force would just need to be double the average, because the average force would be the spring force at full compression, which would be Fs, plus the spring force at 0 compression, which would be 0, divided by 2. And so you would just end up needing to multiply the average force by 2 to get the spring force at the maximum compression. I think that's a bit of a disaster. Also, there's a question about whether they would accept that or not. Having said that, you should just try something here, because the College Board puts out a document after every single AP test where they go over answers that kids give. And this is an answer that a kid gave on this test the year this test was given. And they wrote, for A1, the spring constant can be determined by measuring the time it takes for the ball to travel a fixed distance at different compression levels of the spring. That's not really a principle or a law. That's just like a thing a spring does. Notice they end up using the period of a spring equation to go ahead and solve it for K. Now, if you go down to the commentary they give about this answer here, it says Part A earned 2 of 3 points. There is not a valid physics principle in Part A1 to agree with. However, an equation in Part 2 that contains K is written with measurable variables and correctly solved for K. Even though this equation is not used in the procedure later, these parts are graded independently. And so even if you just solved any random equation for K, they're giving points for that. You gotta try something. Having said that, from what you've learned this year, I would hope it is clear enough to you that the most obvious principle would be conservation of energy, because that's an easy way to derive an equation for K. Now, of course, this all leads directly into the next part, because the next part of this question is about the design. And as I have mentioned many times now, the design comes entirely from the equations. So what they want you to do here is for you to design an experimental procedure to test the hypothesis in which the student uses the launcher to launch the sphere. Now, like I said, Hooke's law could be argued to be viable. They may not think it is viable. It does not say anything about it in the scoring guide. Somebody grading your test could argue for you that if you really say all of those things about how the acceleration is not going to be constant, but you can find the average, and that'll let you find the average force, which can let you find the spring force. It's a lot of work, though. Conservation of energy is much more straightforward. First here, they want you to list the quantities and the associated symbols that would be measured in your experiment. So using my method, notice here, I think this one is a little more straightforward. You have m, delta y, and x as the things you would need to measure. So I'm going to go write that in the table, m, delta y, and x. Now, of course, m is the mass, delta y is the height above the barrel, and x is the spring compression. Now, the equipment that you use for this measurement is really easy. For the mass, it's going to be a triple beam balance. And for delta y and x, these are distances. You measure them with a meter stick. And that's why I think this experiment, using the potential energy version where you tilt the launcher vertically, is a lot more straightforward, because you don't need crazy equipment to be able to perform the experiment. And so the analysis part is going to be pretty straightforward. And so is the describing the procedure part. Pretty much you're just going to kind of be like, well, you use a meter stick and you measure the distance. Like, reading a meter stick is not rocket science. Having said that, I do think it is totally reasonable to use this equation as well. And so notice, using this equation where you're basically saying the elastic potential energy is converted to kinetic energy, the only thing that you would have to measure differently besides this equation, of course you're not measuring the height, is you'd measure the velocity or the speed of the sphere as it reaches the end of the spring compression. And so we can say here, we'll measure the speed, which is given the symbol v, and you can use a motion sensor or a photo gate. Now, there are a lot of methods for this experiment that they end up describing in the scoring guide. So let's go look at some sample charts that they gave here. Now, there are a couple of things we can say about this. This document has all the scoring guides too. And so the measurement section here gives you a point for listing appropriate equipment that matches all measured quantities in the experimental procedure. Now, notice it says here, this point can be earned if the sphere is not launched. Since they underlined something about the sphere being launched twice, you should have realized that you had to say this. Now, notice the rest of these parts are for the description of the procedure thing. So let's just look very quickly at these sample charts. This one is talking about measuring the mass of the sphere, the spring compression, and the launch speed of the sphere. Notice they give a triple beam balance for the mass, a ruler, I think you should say meter stick, but a ruler just works fine for the spring compression because the spring compression distance is going to be small. And then for the launch speed of the sphere, they talk about using a motion sensor. Example procedure 2 uses more of a projectile motion kind of thing, as you can tell. And so it says they're using the mass of the sphere with a triple beam balance, the horizontal spring compression distance here with a ruler, and then the horizontal and vertical displacements of the sphere in this projectile motion sense using a meter stick. Example procedure 3, mass with a triple beam balance, spring compression with a ruler, and then the height of the sphere with a meter stick. That's what the charts should look like. You only get 1 point, and notice it says relevant and appropriate equipment. So the key here is to just really know what you're talking about, know your plan, and be clear about your plan. That's the basic idea. Now, of course, the next part of this question wants you to describe the overall procedure. You want to refer to the table, it says, too. So it says, describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances, referring to the table. They want you to talk about measuring the things you said you were going to measure. Provide enough detail so that the student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. We're going to talk about that part later, too. As needed, use the symbols defined in the table and or a simple diagram of the setup. So this is what I wrote here. I wrote, since the equation for the spring constant, I think you should lead with your equation. The equation is key. Since the equation for the spring constant says K equals 2mgh, I just wrote h here instead of delta y, over x squared, the spring constant is based on the mass, the height, and the spring compression distance. To measure the mass, we can use a triple beam balance. We can vary the spring's compression distances using all 3 pin positions, A, B, and C, and measure those with a meter stick. Since changing the spring compression distance will change the height reached by the sphere, we can measure the height reached by the ball above the launcher using a meter stick positioned at the barrel of the cannon. We can perform multiple trials at each pin position to measure the compression distances and heights and average them together. We can then use these values to determine the spring constant for the launches from each position. So we do a bunch of measurements at position A, average them together, get an A value. Do it for B, average them all together, get a B value, and then a bunch of trials at C, average them together, get a C value. Now, of course, if you were talking about the kinetic energy process, that would be slightly different. As shown here in the sample document, if you use just like a straight up energy conservation thing, they said the mass of the sphere is measured with the triple beam balance. The launcher is aimed horizontally on a level surface toward a motion sensor. The spring is compressed to position A, and the spring compression distance is measured. The mass is launched. The motion sensor measures the launch speed. The process is repeated 3 times at position A. The procedure is repeated with the spring compressed to pin positions B and C. For example, procedure 2, the launcher is aimed horizontally at a height above the ground so that the sphere will follow a projectile path and land on the floor. The spring is compressed to pin position A and the sphere is launched. Measure the mass of the sphere, the initial spring compression, and the vertical and horizontal displacements of the sphere from release to landing position. Repeat 3 times at pin position A. The procedure is repeated with the spring compressed to positions B and C. Now, what I think is weird about the example procedure that they gave here is they didn't actually talk about using the equipment. I really think you should use the equipment and talk about it in your procedure. Measure the mass of the sphere using a triple beam balance. Measure the initial spring compression using the ruler. Just make it clear to the person who is grading your paper that you know what you're talking about. For the scoring guide here, there were 5 points. We already talked about the first one, listing relevant and appropriate equipment that matches all measured quantities in the experimental procedure. You want to describe measurements of the quantities sufficient to determine the spring constant. That all comes from the equation. They give you a point for a plausible procedure. In other words, it can be done in a typical high school physics lab. You're not talking about like a particle accelerator or like some fancy piece of equipment you're never going to have that involves launching the sphere to determine the spring constant. They give you a point for launching the sphere from at least 2 different initial positions. Now, let's stop there for a second. Why are they talking about that? They're talking about that because you have to compare the spring constant at different spring compressions, or in other words, at 2 different pin settings, A, B, or C. And so you can't get enough data to determine the constancy of the spring constant at these different pin settings unless you do it at least 2 different initial positions. Since they gave you 3, I would say just do all 3. You don't actually have to do it. You just have to talk about it. Then notice here it says, any attempt to reduce uncertainty will get you a point. The classic example of that is multiple trials at a pin setting. If you just talk about doing multiple trials and averaging them together, they're going to give you the points for that. Now notice here, if you're talking about just like compressing the spring with a force sensor, so you're not launching the sphere or something, you can earn the first, second, and then 5th point. You lose these 2 for the plausible experiment and the launching of the sphere, but you can still get 3 out of 5. I want you to take a minute to pause this video here and make sure you really understand 2 things. A, what the scoring guide is getting at, and B, what it is you said and how it relates to any of those 3 example answers that have been given so far. When you hit play, we'll move on. All right, now I want you to take a note here. This is very important. In any procedure description, there will always be a point given for reducing uncertainty. They'll almost always give you this point for talking about conducting multiple trials. This will really involve you in varying the independent variable so you can get more measurements of the dependent variable and doing that multiple times. Let's take my example. I am varying the independent variable, the spring compression, so that I get different heights, which I can then use to calculate K multiple times. If I just talk about, putting it at position A, getting a height, putting it at position B, getting a different height, putting it at position C, getting a different height, that will give me 3 numbers. It'll give me 3 pin positions. But doing multiple trials at each of those pin positions is what's going to get you this point. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So moving on, I just want to show these example responses that they gave in the scoring guide. Again, just make sure depending on whichever one of these you did, that you have all of the appropriate details. Notice this one we didn't talk about because this was the one that I wrote. You can aim the launcher vertically, compress the spring to pin position A, launch the sphere vertically, measure the mass of the sphere, the initial spring compression, and the height, and then repeat the 3 times at pin position A, and then you're repeating the procedure with the spring compressed to positions B and C. So notice you're repeating 3 times at position A is what's going to get you that point for reducing uncertainty. If you want to look at these, I would pause here. Moving on to part C here now, which is always going to follow up this experimental procedure description part of an experimental design question. It says, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. Now, this is the part of this question that gets a little wonky, because usually what I tell you, and remember, there at this point should be roughly 2 equations that you're using to calculate K, whether it's mv squared over x squared or K equals 2 mg delta y over x squared. Usually what I tell you is if you graph the variables in the numerator on the y-axis and in the denominator on the x-axis, the slope will be equal to the thing you're looking for. In this experiment, because you're trying to determine whether that thing is constant at just 3 positions, that might not be the most efficient way to go about it. I usually say it's a bad look to just say, I'm going to get all this data and then I'm just going to do a bunch of different calculations. You might as well just make a graph. Here, it might not be the best idea to make a graph. Now, of course, if you do make a graph, you really just have to talk about the graph being and staying linear at these different compression distances on the x-axis. That would be sufficient. Having said that, just using the equation to get a K value with the height and spring compression, or speed and spring compression, of course, these being the average values, at position A, B, and C, and then just comparing those 3 numbers, I think would be sufficient. Here's what I wrote. I wrote, since we have spring compressions and maximum heights for each pin position. Now, notice this would be multiple spring compressions, multiple heights. They're all probably going to be pretty close, you would think, over the multiple trials, but that's the idea. We can calculate an average spring compression and maximum height for each launch position. We can then use these data to calculate the spring constant for position A, the spring constant for position B, and spring constant for position C. Now, we already know these are going to be the same. And so we can just say here, we can then compare these values. If they're the same within experimental uncertainty, the hypothesis is correct. And if they're not, then the hypothesis is wrong. Now, of course, the graph is fairly viable, but I would say maybe it's not the best move. Now, of course, if you chose, which I'd imagine is probably a decent amount of you, if you chose to use this equation, your answer should look relatively similar, except you'd say, like, well, I figure out what my average launch velocity for A is and my spring compression at A, do the same thing for B and C, and then just calculate K at position A, K at position B, and K at position C. And if they're the same, then the kid is right. And if they're different, the kid is wrong. This part gave you 2 points. You had to compare the measurements of the spring constant or a suitable proxy at all 3 possible compression distances A, B, or C. And you had to consider uncertainties in confirming the hypothesis, meaning if the numbers match with experimental uncertainty or if the numbers are about the same. Now, this is an important thing because you're just going to get some experimental uncertainty in your answers. And so they want you to mention that because, like, let's say the spring constant is 1067 newtons per meter. If at A, you get 1067, and at B, you get 1068, and at C, you get like 1065, that doesn't mean the spring constant is different at all 3 positions, and so the hypothesis is wrong. It means you had some experimental error, and that's pretty good. That's an important thing to realize. This is another thing to realize, is that if they want you to compare values for multiple trials here, you have to talk about the numbers matching within experimental uncertainty, that they're close enough. Take a second to pause this video here and make a note of that, making sure you understand all the parts of this scoring guide. And when you hit play, we'll go through some example responses. Now, just before we move on very quickly, I just want to make sure that everybody understands this note here. Notice it says the second point of part C is not earned for saying if the numbers are the same. You have to talk about them being like reasonably close, because you're never going to be able to repeat this at all three pin positions and get the exact same number. That's an important thing to realize. You could also talk about sig figs. Like if to a certain number of significant figures, the measurements are the same, then it's good enough. It's important to remember in the lab, which you really didn't get a taste of this year, close enough is good enough. There's always going to be some experimental uncertainty. Now, looking at the example responses here, for this first one, and this was just like the straight up conservation of energy using the speed, for each pin position, take the average V launch average of the launch speeds measured at that position, calculate the spring constant using the energy conservation relation. Notice that's basically what I had on the other slide, mv squared over x squared. Compare the k values for each spring position. If the values agree within experimental uncertainty, then the hypothesis is confirmed. Now, notice the horizontal projectile method is kind of a pain, because here you have to talk about how you use the projectile motion stuff to calculate the speed, and then use that in the conservation of energy relation. It's fine, but it's a little longer. Now, of course, that response for the projectile motion ends here. My method, which was talking about the maximum height thing, is shown last. For each pin position, take the average height for the maximum vertical sphere displacement, use conservation of energy to calculate the spring constant K from the equation. Now, notice here it says use that equation, 1/2 kd squared equals mg delta y average if measuring the height from the release or pin position, or 1/2 kd squared equals mg delta y average plus d if measuring the height from the spring's uncompressed position, and then compare the k values. The only part that's a little confusing about that is you really want to measure the height from the place where it has no spring energy anymore, and that's basically going to be like at the end of the barrel. That's because that's where the spring fully decompresses. If you use the phrases like a launch position, that works just fine. Now, moving on to the last part here, part D, it says another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after the other. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere the instant it loses contact with the plate. On the axes below, sketch a graph of the launch speed as a function of sphere mass. The other day, we did a problem where two objects were being pushed up a ramp. And the first part of the question said, what does a graph of the velocity look like as a function of the position? And as I mentioned, you are going to be asked about the shapes of graphs. The shapes of graphs determined by the equation. So here, if this thing is being launched, then the conservation of energy relation is going to be initial spring energy equals final kinetic energy. 1/2 kx squared equals 1/2 mv squared. And what you get when you solve that for v is the square root of kx squared over m. What that shows is the velocity is inversely proportional to the square root of the mass. Now, you should have a sense of what an inverse relationship looks like on a graph already, but if you don't, remember, you have a calculator. Use your calculator to determine the shape of the graph. Notice that's what I was just telling the honors kids. If you plot here y equals 1 over the square root of x, now you'll be able to see that relationship. And if you graph it, it looks like a traditional inverse relationship, this sort of exponential decay style of graph. And so here, you're going to want to be careful when you're drawing this because it has asymptotes. But basically, if you just sketch it like this, that's good enough. And so notice the scoring guide here gives you 1 point for a curve where the launch speed always decreases with increasing sphere mass, and a curve that is entirely concave up and has a launch speed always decreasing with an increasing sphere mass. So notice, if you show a graph that looks like this, where the launch speed always decreases with increasing sphere mass, they might give you that point. But I think it's important to realize you want to make sure you're being very careful about that exponential decay, because if you end up showing this thing hitting 0 at the end, like this, or being constant, like perfectly straight for a while, they might be nitpicky about that second point. But that's the idea. Take a second to pause this video here and make sure you understand all aspects of this part of the scoring guide. And when you hit play, we'll move on. Just to be clear, in case you didn't draw that exact graph here, we can go to this document. Notice here, the first kid who did this question used exactly that idea that the speed is inversely proportional to 1 over m, did that part, got the points. This kid, who knew a little bit less, drew a straight line, and this kid just did this totally backwards. I'm assuming that kid probably got 0. For the middle kid here, what does it say for part D? It says part D earned 1 of 2 points for indicating that the launch speed decreases with the increasing sphere mass, but did not earn 1 point because the graph is concave up. So they would have given you 1 of 2 for that. Part D earned 1 of 2 points for indicating that the launch speed decreases with increasing sphere mass. Really? Oh, wow, that's stunning. That's really wrong. So notice here, they give you 50% of the points, which is enough to earn you a passing grade on this test. If you are completely wrong, you gotta try something. That's a really important thing to remember. Now, these experimental design questions are not easy, but if you follow the idea that the equations are key, you should be able to do enough to earn a reasonable amount of the points. All right, everybody, that is it for today. Have a good one.